Today's lecture is dynamic time warping, DTW. It is a technique widely used for aligning time series data and is commonly employed in recent research. When the lengths of two time series data are different, one approach is to adjust their lengths by upsampling or downsampling one of the series. However, this method may not always be reasonable. An alternative that has emerged is DTW. The principle of DTW is to match similar pattern between two time series data. For example, as shown in this diagram, DTW align peak with peak and down peak with down peak, thereby transforming the time axis accordingly. DTW is carried out through four main steps. First, calculate the distance matrix. 2. Calculate the cumulative distance matrix. And backtracking and verify the matching path. While it is possible to implement it easily by importing library in actual coding, I'll explain the process nonetheless. First, the distance matrix is calculated. For example, A time series A is 134 and B time series B is 1344. So this component is distance between this one, and this one is the distance between this one. And next step, using the previous calculate distance matrix, the cumulative distance matrix C is computed. This process is somewhat complex. For each component, the algorithm compares it with the element to its left and the one diagonally left above and the one directly above. This component compare with this one, nothing, so just 0. This component compare this one. The smallest value is 0, so 2 plus 0, that's this one. And this one, smallest value is 2, so the result is 5. And let's see this component, compare these three value. 0 is the smallest value, and then add this one, so this value comes out. So let's adjust this one. 0 is the smallest value, so 0 plus 1, this is the cumulative matrix. So then add the smallest of this value to the original element. In this way, we can easily get this cumulative matrix. Finally, there is a backtracking. Starting from the bottom right element of the cumulative distance matrix and trace back to the top left component. This path is determined by following the smallest value at each step, 0, 0. Of course, there can be another number, not 0. Just follow the smallest value. Based on the result of backtracking, the DTW path is finalized. In other words, the time series data A and B are matched as follow. This one, this one, this one, this one. Based on this backtracking data. The third and fourth element of B are effectively considered as a single element and are matched with the third element of A. So let's go implement the real code. To implement DTW, firstly, you should install the DTW Python library. Using that, you can import the library of DTW and import the basic library and DTW library. And we make and generate time series 2 data and visualize. You can visualize like this one. I'll upload the entire code. So this is the two time series data and some difference between them. And this is DTW. We can alignment using this function, and then we can visualization DTW. Of course, in real code, you don't need to show this one. This one is for just lecture, not real code. So using DTW, we can easily know the matching part and matching segment between two time series data. So using that, you can visualize the result of DTW, and then let's match. So transform the time series data based on the DTW path using this one, and you can visualization the transform time series data. So by aligning this one, the two different time series data match like this one. So when you see that, the similar part match each other. So this is the entire code of DTW. So when you solve the time series length problem, you can easily use this one, and it's very powerful algorithm these days.